Hello, here's a question on collisions where we're going to be bringing impulse into Newton's laws, which is, how we're starting off in collisions, really getting used to this new terminology. And they start with this in the question, so they want to state in words Newton's second law of motion. Right, good way of doing any of these state in words questions anyway is to have the formula in mind. So our force is the rate of change of momentum. This is the thing that we're really wanting to describe here. That is our Newton's second law. So we want to say what the terms are really, and then bring in the fact that they're vectors. So we can start off by saying, let's start with the right hand side, the rate of change of momentum, and that has to be attached to something. So we're going to say of an object. Something has to be possessing this momentum, is equal to equal to, proportional to, whatever way you want to do it. I mean, in this case, our constant of proportionality is 1, so we can say equal to so that's the net force. It's not just any old force, it's the net force. It's our resultant force, so you could even say that means the same thing. Acting on or exerted on, acting on that object. So we've got most of it down here, as we said, what the right hand side and left hand side are, but remember we've got vectors all over the place here. So we need to also put in and in the same direction. There's no minus sign thrown around in here. So the direction of the force and the direction of the change in momentum are the same. So the rate of change in momentum of an object is equal to the net force acting on that object and in the same direction. So although that sounds relatively complicated, maybe, and a lot to remember, all we're really doing is learning how to describe a formula. Say what is on each side of the equation and then bring in direction if it's got vectors. So that's fine for part A. So for part B, they're getting us to do some calculations now. They've given us these masses and the velocities provided. Two objects A and B moving directly towards each other. They stick together on impact. So we know we've got E of 0, not that that's going to come up in this question, but we also know that that means it's inelastic. So we can't go to conservation of energy here because the kinetic energy is not conserved through the collision. After the impact, we move with common velocity V. So we can't use conservation of energy, but we can use conservation of momentum. So we'll go with that. Our momentum beforehand, remember these are all vectors. So we've got 3 times 5 for mass times velocity for A. We'll take positive going off to the right. So we've got a -2 for the velocity multiplied by 7. And that is going to be equal to the total mass once they've stuck together, which is 10. Times V. So we've got 15 minus 14. So V is going to be 0.1. It's going to be our 1 divided by 10. I mean, I've already put that that's positive, but I'm going to be doubly sure and say that that is to the right, that 0.1, just to make sure no one's getting confused. But really, by saying positive here with this arrow, 0.1 as a positive answer should be sufficient. But that's just doing a straight conservation of momentum, and there you go. We've worked out what's going on the other side of the collision. So determine the impulse of the force experienced by the object A and state its direction. Well, we know the direction must be to the left because B is going to the left when it hits A. So A is going to have a change in momentum, which is heading off to the left. So we know, first of all, before we've even done anything, impulse to the left, which is going to be the change in the momentum. And the momentum of A has gone from 15 beforehand, 3 times 5, to 3 times 0.1. So we have to take that off. So that's 14.7 Newton seconds is our impulse to the left on A. And of course, we're going to impulse. You can see how this is useful because it's packaging up that we don't know what the force is of the impact between A and B. We haven't got any measure on that. and we don't know what the time of the collision is. So these two things, the F and the T in our equation here, we don't know. So we're packaging this all up into impulse, because the only thing we do know is the change in momentum. So we know P and not F and T. So that's why impulse is useful on this, because it sort of, you know, gets around these two unknowns that we've got. Right, explain using Newton's third law of motion the relationship between the impulse experienced by A and the impulse experienced by B during the impact. Okay, so Newton's third law, that is telling us that the force of A on B is equal to the -1 times the force of B on A. So the forces are equal and opposite that they're exerting on each other. The force exerted by A on B is equal and opposite to the force exerted by B on A. So we've got that from Newton's third law. We also know, we can say also, the time of impact is going to be equal for A and B, because, you know, they're hitting each other, so they must have exactly the same impact time for A and B. So this is telling us quite a lot here, that we can say the integral of f dt for A is the -1 times the integral of f dt for B, because dt is the same. You know, we've got the same limits on these integrals. They're both going from 0 to t. F is of the same magnitude. They've just flipped sign for each one of them. So we know those are the same. So that was a therefore off of the previous two statements. And then we got another therefore, because the rate of change of momentum, or the change of momentum, I should say, not the rate of change, just the change of momentum for A and B is equal to these integrals. So the impulse on A is -1 times the impulse on B, i.e. they are equal and opposite. So that equal and opposite is just flowing all the way through this. From Newton's third law, it flows through to the impulse, because we're just packaging up that unknown force. The force is described by Newton's third law, or the relationship between the two forces experienced by A and B. We're packaging that up into the impulse, so it's naturally just going to flow all the way through, and that equal and opposite then appears in the impulse as well as in Newton's third law. So yeah, that's a nice way, this question, of getting into this new terminology and seeing how really this is just a new way of describing, or a new way of talking about Newton's laws, when we've got unknowns both in force and in time, and then describing everything in terms of impulse. So yeah, it's a nice starter question.